Hey guys, welcome back to class, and today we're going to be talking about Charles' law. Charles' law is the relationship between volume and temperature. The equation looks like this. Your initial volume divided by your initial temperature is equal to your final volume divided by your final temperature. Here's the equation. I want to give you a quick rundown of what Charles' law actually is before we get into it. Charles' law really is, this is a way to explain it. Let's say you have a balloon, right? A little wimpy balloon that you didn't blow up very much. Inside the balloon, it has air molecules, gas molecules. And these gas molecules are moving around. And for the sake, let's say they're moving, for the sake of this example, let's say they're moving around at a small speed, right? So I'm going to draw little bitty arrows to show their tiny speed. Now, let's say what I do is I set this balloon, I put it over a fire. I put it over a fire. Right? And it gets really hot. Well, what happens to those gas molecules inside the balloon? Those gas molecules begin to speed up. Those gas molecules speed up and move faster. And what that does is it causes those gas molecules to collide with the sides of the balloon a lot harder and faster, and it causes the balloon to expand. So let's draw the arrows longer because now they have more velocity. Each gas molecule is moving now with a greater velocity and hitting the sides of the balloon, causing the pressure to go, causing the volume to increase. Now let's say I take that balloon and I put it on ice. Right, I put it on a couple blocks of ice. And let's put some little melting little nuggets there. Okay. And I put the balloon on top of ice. What's going to happen? That was terrible. The balloon is actually going to decrease in size. The volume will go down. It'll have the same number of gas molecules in here. I didn't lose any gas molecules. I didn't open up the balloon and let any gas out. It has the same number of molecules. They're just moving at a much, much slower speed, so the balloon's not expanding as much. So what happened in each example? First, we raised the temperature of the balloon, and that caused the volume to increase. Next, we lowered the temperature of the balloon, and that caused the volume to decrease. And that's the relationship between temperature and volume. It's a direct relationship. As one goes up, the other goes up as well. Now let's get into the notes. The notes, you're going to click right here. Now the way the class is, like normal, I have the objective up here. The video that's not made yet will go here. The notes I'm going to be talking about are here. You download these and go over the notes with me. Here's any practice problems that you may or may not need. You do as many or as little as you like, and then I'll have a link to the test down here as well. So let's get into the Charles' law notes. Okay, Charles' law. It's the same steps as Boyle's law. All the gas laws, we're going to follow the same steps. You pull out your data from the word problem. You create a working equation, and then you're going to check for units. So first of all, we need to talk about the starting equation. The starting equation, as I mentioned before, is volume, the initial volume, divided by the initial temperature. Let's fix that. Your initial volume divided by your initial temperature is equal to your final volume divided by your final temperature. And what does this graph look like? Well, it's a direct relationship. As one goes up, the other goes up. So if I have volume and temperature here on the graph, on the x and y axis, and I were to graph volume and temperature, I would see a linear relationship. As one goes up, the other one does too. And pretty much all of these have the same linear direct relationship with the exception of pressure and volume, right? Our Boyle's law was the exception to this rule. Okay, make sure you got these notes. I'm going to move down. And I'm going to be smart this time and do that. Okay, So now let's read our problem. A gas has an initial volume of 30 centimeters. If the initial volume is 30 centimeters, well, that's our V1. 30 centimeters. And that's not just 30, it's 30 dot centimeters. That tells me I have two significant figures there. Centimeters cubed. Because it's not just the length, it's a volume. Volume is a length cubed. Or a distance cubed. Now, it says the volume is decreased to 7.5 cubic centimeters. So that's 7. That's my final volume because it goes to that, right? That's the second part of this problem. Right? 7.5 centimeters cubed. That's two significant figures as well. And the next part, what a lot of people forgot on yesterday's problem, that one was dealing with temperature as well, Gay-Lussac's law. If the gas was originally at 50 degrees Celsius, well, whenever you have these degrees Celsius, we don't calculate gas laws with degrees Celsius because degrees Celsius has negative values, and we don't like to put negative values in these equations. So we convert these to Kelvin always. So in order to convert to Kelvin, you have to do 50 plus 273. And you should get 323. 323 Kelvin. And I'm going to put that here. It says if the gas was originally 50 degrees Celsius, so that's my initial temperature. Originally, right, or initially, it was 323 Kelvin, and I don't know T2. Remember, I told you, I'm going to give you guys 3 of the 4 variables, right? All you got to do is plug them in. Now, the issue we have here is that we're solving for temperature, and temperature is in the denominator. And we never want to solve for something in denominator. It adds too many steps. So the first thing we do, if you remember, is we flip this equation, right? We put temperature on top and volume on bottom. So I'm going to rewrite that as, it's not equal to. I can't write an equal sign. I'll just put a little arrow here. Okay, we're going to rewrite that as T1 divided by V1 is equal to T2 divided by V2. If you flip the top and bottom, this is still a true statement, right? The numbers are different, but it's still a true statement, so the equation works. Now we're going to plug, we can't plug these in because we want to solve for T2. We want to get T2 by itself. The way you do that is you multiply by V2 on both sides. Multiply by V2 on both sides. So then you're left with V2 times T1 divided by V1 is going to equal T2. Now, V2, we just plug these in. V2 is going to go right here. T1 is going to go right here. V1 is going to go right here. And T2 I will put right here. V1 is 30 dot cubic centimeters. V2, I put that in the wrong spot. V1 right here is 30 dot centimeters cubed. V2 is 7.5 centimeters cubed. And T1 is 323 Kelvin. 323 Kelvin. And we don't know T2. We can put a question mark here, or just leave it blank for now because we're going to fill it in. Now all we do is put this in our calculator. We put 7.5. So I'll do it in my calculator. 7.5 times 323 divided by 30. And the answer we get is 80.75. 80.75. And something you always want to remember is a lot of people are still forgetting this. You don't want to just put the answer as 80.75 for 2 reasons. Number 1, that's 4 significant figures, and I want the same number as my lowest number of significant figures. Here I have 3, here I have 2, and here I have 2 significant figures. So my answer is going to have 2 sig figs. That's 1, 2. The 7 is not significant, but it follows the last digit, and the last significant figure is a 0. The 7 rounds up the 0 to a 1. So your answer is 81. But I need to know my units. So you can always calculate your units separately. You could leave these out here and calculate them over here separately. I have centimeters cubed times Kelvin, so times Kelvin, divided by centimeters cubed. Centimeters cubed. Cross those out, you're left with Kelvin. So my answer should be Kelvin. And what was I solving for? I was solving for temperature. That's the unit for temperature is Kelvin. So that's the correct answer. Now remember, your test question is going to look very similar to this. The numbers are going to be different. So as long as you can follow this method, you guys are going to be fine. As always, make sure to email me if you have any questions. And have a great day.